DNA, the very thing that links us together, like a ladder trying to impersonate a fancy staircase. It's rather impressive just how much of us can be linked to these helices. It wouldn't seem wrong to assume they've been around since the start of life itself. However, to such a notion, this is likely not the case. Let us first take a swim in the primordial soup, the zone where our great-grandparents probably floated within, not knowing what a mess they'd be responsible for. For the sake of visual ease, I've minimalized how the basic particles in this soup should look for the sake of making a point. Assuming the conditions for an RNA world, we can imagine these basic nucleotides and bases starting to link up and form their own strands. How these link up, we have no clue. That's why it's a theory, not a fact. So, assuming a magic backbone linking force for now, congrats, we've got a molecular spaghetti. Now, the purpose of these strands of RNA may vary. Honestly, generating long strands in general are rather difficult. They have a 2' OH group on their backbone, like a self-destruct button capable of base-catalyzed hydrolysis, which is fancy speak for a good chance of being cleaved at any point. Though, it is hypothesized there is a chance of ancient RNA able to methylate other RNA to stay better protected, but once again this is a hypothesis. Well, assuming safety from cleavage, these RNA strands are now set in a path where they could perhaps utilize the free-floating bases to possibly replicate or make an addition towards the development of other functional structures. Of these potential routes, due to RNA's rather unstable nature, its random properties actually demonstrate an evolutionary pathway where, because of the concept of base variants, these structures can form via folding with different uses and even compete. For the sake of simplifying things, these various structures can range from what's basically structures that can create to those which destroy, with of course room for the in-between. For those regarding such capabilities, we can relate to the very ribozymes we witness today. It's probably these very structures that lead to our hypothesis of this RNA world, in the first place where a sort of enzyme is given function by just RNA alone. The best example is RNase P, one of the first ribozymes discovered, which is responsible for cleaving the 5' end on pre-tRNA to make it mature. This isn't simply vaguely linked. There have been various cases in labs where, upon selecting for RNA capable of putting together nucleotides, their artificial evolution process via PCR machine have led to far more efficient stages. All that remains then is for the test of time to take its place on our potential candidates of RNA ancestors. It isn't a straight shift from RNA to DNA, of course. As the RNA sort of stabilizes, soon the formulation of these ribozymes could lead to the formulation of amino acids and then proteins, all of which serve to further complicate the abilities of pioneer life until at some point DNA's traits are selected for the sake of its stable properties. Let's just see that in motion. Well, as you had seen, DNA would be the future steps that awaits its primal stage of RNA. From its stability and safety, it was of course the most fit candidate for storing instructions for the development of our fundamental aspects of life, such as proteins and their enzymes. Really, in regards to RNA, its issues even stem from its utilization of uracil. In standard DNA, cytosine has a tendency to deaminate, leading to uracil, creating instability in the DNA chain. In the case of success, simply removing uracil altogether from DNA was its safest bet in keeping the strands maintained. However, uracil is still useful as it is a more simple form of a base that ends up remaining in the RNA, as it serves a more intermittent frame of function within cells where this deamination process doesn't have enough time to occur while being cost efficient. Considering all the facts, it would seem as if we've mapped out the origins of life's pathway, no? I mean, we've witnessed a primal RNA capable of formulating the steps of life, taken further by the safety rails DNA provides, right? However, to such a statement, there is a whole realm of nuance. See, in having this theory properly function in the first place, we have to both assume the capability of RNA linking up over time with some unknown force to then somehow survive in the improbable conditions of their chains lasting for the long term. Such a thing makes us a bit more open to reviewing than we wish, and as such, this theory remains with others to serve another alternative. Let us then enter the primordial soup of an alternate case. Another widely reviewed theory finds itself in the metabolism-first hypothesis, where perhaps the ability to formulate complex compounds founds itself before that of these RNA-based hypotheses. In one version, the formulation of particles such as amino acids and other complex molecules, formed via mass chemistry of the primordial Earth exists. This version, however, developed potential issues in what is the tar paradox, creating large gaps between the many molecules, making interaction rather difficult. Alternative from these complex compounds would be of things like, for example, acetate, founded from carbon dioxide and hydrogen gas in a reverse Krebs cycle among other metabolic pathways used to witness thermodynamically favorable reactions in making compounds. These compounds would then demonstrate a step upwards in a chain of increasing complexity. We could be seeing what are fats, sugars, and proteins as even greater steps in such a direction without the issue of junk material due to the favorable reaction process. The benefit of such a theory is that it avoids the complications found in the RNA world. We don't need lab-based linkage between the nucleotides, and we aren't as susceptible to the breakdowns faced in the RNA world. However, it is found to be lacking in the experimental side of things, being largely based on a generalized study. Such a theory presents locations as to where potential life started its bloom, like for example the iron-sulfur world theory, where perhaps iron sulfide deposits by deep-sea vents aided in the catalysis of complex reactions using energy from the vents. Such a concept serves as a reference to both suggesting towards the metabolism first theory while aiding in improving our understanding of places able to start the origin of life itself, perhaps even alternate theories. Speaking of such a thing, there do of course exist other more obscure sorts of theories. For example, the RNA peptide coevolution theory, suggesting a peptide RNA world with peptides forming, capable of serving as enzymes in the development of RNA strands, which would serve as the fastest means of evolutionary development, however leaving twice as many questions from the fusion of theories wondering how either is replicated. Then is what I'd classify as a band-aid solution, the Panspermia Hypothesis, where perhaps life itself had come via foreign sources such as meteors or comets, leaving behind their organic molecules as their hitchhikers. Such a thing would be an insane head start on the development of life itself, but it'd also be dodging the true question of life's general origin. I mean, we are still rather curious about just how these initial bits of matter came to be in such a theory. So, life's origin is still a large question at hand. Perhaps we've solved it in the most popular theories. Perhaps there are things we haven't even once considered, and perhaps we have a long way to go. Regardless, the study of life's origin, while it may not pinpoint us towards the starting line, it is the very thing that has taught us about ourselves beyond what we've accepted at face value.